Now, remember that when we studied KCL and KVL in a systematic fashion, using graphs of circuits, we have realized that once you know the node voltages of a given circuit, you can easily compute all the branch voltages from those node voltages. Okay? And since in general the number of node voltages of a circuit is much smaller than the total number of branch voltages, therefore it seems to be a very good idea to attempt to formulate a circuit in terms of node voltages. Okay? And node voltage analysis method does exactly that. So the idea is to solve for node voltages. Okay? And for that we require equations, and those equations are coming from KCL constraints applied to each node except the ground node. Okay? By writing KCL, or applying Kirchhoff's current law constraints at each node except the reference node or the ground node. Okay. Note that once we solve the node voltages, we can easily obtain branch voltages, and once the branch voltages are known, since at least at this point we're considering LTI resistive circuits, we have a bunch of resistors, and using Ohm's law we can figure out all the branch currents, so everything will flow smoothly. Okay. Note that once the node voltages E1, E2, E3, and remember that we stacked all those node voltages into a vector which we called node voltage vector, and which we denoted by letter E. Once the node voltages contained in the node voltage vector E are known, branch voltages which make up the vector V can be computed easily. Okay. Remember the relation V equals A transpose times E, and A was our reduced piece in this matrix. And once the branch voltages are known, the branch currents can be computed by terminal equations. Basically, we talked about Ohm's law. Now, the main idea is here, but there's some details we have to be careful about, and we will go over those details through certain examples. Okay, so let's begin by the first example. Here is our first example, where we're given a circuit, and we will try to formulate the circuit in terms of node voltages. Okay, so let's do that. Suppose the circuit we're given is this. Okay, we have a current source, a resistor, another resistor, another resistor, another resistor, and another current source. Then here we have a parallel resistor. Okay. So this is IS1, R1, R2, R3, R4, R5. This is IS2, the current of the second current source. Now, what we want to do is, we want to apply this method here, and by which we mean, let's formulate the circuit in terms of node voltages. Okay. Of course, when we want to formulate a circuit in terms of something, we have to be clear about what we mean by the formulation variables. So unless they're already given, what we need as the first step, or even the 0th step, we have to do a very proper labeling. Okay. So we're going to apply node voltage method. So what we have to do therefore is, there is a procedure, is first choose ground node. Okay. With respect to which we measure or define all the remaining node voltages, and then label node voltages. Okay. And finally, once we have the node voltages properly labeled, we start writing KCL at each non-reference node. And one step is write the constraints imposed on the currents by Kirchhoff's current law. Okay, so let's choose a reference node. Let's choose this node as our reference node. So that's our ground node. Okay. Ground. Okay. Reference node. So besides that node, we have 1, 2, and 3 more nodes. So that means we will have 3 node voltages, meaning that we will have 3 formulation variables, or 3 unknowns. So that means we have to write down 3 equations. Okay? And then 3 equations in terms of those 3 unknowns should be enough to figure out those 3 unknowns. And once we know those node voltages, we can figure out everything else very easily. Okay? So let this be our first node, this is second node, and this one is the third node. Therefore, this node voltage we label by E1, this is E2, and that's E3. Okay, so this is the labeling part. Once labeling is over, we start writing KCL at each node. Okay. KCL at the first node, node 1. Okay, so let's write our first equation. Now, again, we will follow certain conventions. We don't have to follow them, but if we follow them, things become easier to control, okay, or to see when we make an error somewhere. So the convention is such that at each node, you will treat all the currents as if outgoing from that node, and you will sum all those outgoing currents and equate it to 0. Okay, so this is our first node. So that means we're going to sum this current, and that current all outgoing, and the sum by KCL must equal to 0. Okay. Now what's this current? That current is, now since this current is IS1, this current is simply minus IS1. Okay. So minus IS1. How about this current? This current is plus IR1. Let's call it IR1. The current flowing through R1 in that direction. And finally, how about this current? That current is, let's call it IR2. Okay? And KCL says that the sum of those 3 currents must equal to 0. Now this equation is correct, but it's not in the final form that we want. What we want is, we want to express all those equations in terms of our formulation variables. Okay, and what are our formulation variables? Variables are E1, E2, and E3. Therefore, we want no other unknown, okay, than those three variables, E1, E2, and E3. Now, if you look at this equation, there is no problem with this minus IS1 because it's not an unknown. Okay, we assume that we know all the currents and voltages of the independent sources. Okay, so there's no problem with this term. But IR1 and IR2, they're unknowns at this point. So what we want to do is we want to express them in terms of known voltages. And that is quite easy because IR1 is, by Ohm's law, VR1 over R1. Okay? And VR1 is this voltage plus minus. The voltage appears across terms of R1. Okay? And this VR1 is a branch voltage, and we know that we can easily express branch voltages in terms of known voltages. And this branch voltage is no other than E1 because it appears between node 1 and ground. Okay? So this thing here is E1 over R1. Therefore, instead of IR1, if you write E1 over R1, everything will be fine because R1 is known. We assume we know all the circuit parameters, and the unknown E1 is one of our formulation variables. Likewise, IR2, we want to express it in terms of known voltages. This current is IR2, how we labeled it. Now, IR2 equals this voltage plus minus, let's call it VR2, VR2 over R2, okay, by Ohm's law. And VR2 is this branch voltage plus minus, and this branch is between node 1 and node 2, therefore we can simply express it in terms of node voltages. In other words, this is E1 minus E2. Hence, this current is E1 minus E2 divided by R2. Okay. This is VR2 over R2, and this is E1 minus E2 over R2. Okay. So if we write this equation again in this form, minus IS1 plus, instead of IR1 we write E1 over R1, and instead of IR2 we write E1 minus E2 over R2 equal to 0, everything is fine because all the unknowns are coming from our formulation variable set. Okay, so let's give this equation a number. We will obtain similar equations by writing KCL at the remaining nodes, and then we have the set of equations that we need. Okay. So let's move on to second node. KCL at node 2. Okay, again, we talk about convention where, when we write known voltage equations, where we treat all the currents as if they're outgoing currents from the respective node. So in this case, we're talking about these four currents. Okay, this current, this current, this current, and that current. Okay? And by KCL, some of those four currents must equal to 0. Okay. So this current is this voltage plus minus over R2, and this voltage plus minus is E2 minus E1. Okay. Therefore, E2 minus E1 over R2, okay, which is negative of this current, is simply that current. Then we have this current, which is this voltage, branch voltage over R3, and this branch voltage is, since it's between, this branch is between node 2 and ground, simply it equals E2 plus E2 over R3. Okay. Then we have this current. Okay, it's E2 minus E3 plus minus over R4 over R4, and finally this current is E2 minus E3 over R5. Okay, so that's all the 4 currents associated to the second node, and by KCL, this sum must equal 0. That's our second equation, which again is only in terms of our formulation methods. And finally, KCL at node 3. Now we write the sum of these 3 currents. This current is E3 minus E2 over R4 plus E3 minus E2 over R5, which is this current, and finally this current, which directly equals the current provided by the independent current source, which is IS2, which is known, plus IS2, and that equals 0. That's our third and last equation. We have 3 unknowns, and here we have 3 equations. Therefore, the formulation is over. Okay. So let's rewrite those equations in a nice form, and then we can put them into a matrix form. That's what we will do usually. We'll put everything in matrix form because they look nicer, and also if you want to take software help, let's say, to solve the circuit. For this we don't need software, but consider a very large circuit. In that case we have to take help from the computer, and then when that's the case, computers, they like matrices, and therefore we want to express our equations in matrix form. Okay. In terms of conductances, of the resistors, GK, and GK is 1 over the kth resistance. Okay. Let's rewrite our equations. Okay. Equation 1 becomes G1 plus G2 times E1, okay? Here is G1 E1, here is G2 E1, then we collect those 2 terms and write G1 plus G2 times E1. And then we have minus E2 over R, which is minus G2 E2, and let's throw the knowns to the other side. This is a known, and then we put it on the other side, and it becomes IS1. Okay. So this is equation 1 expressed in a little bit different way. Let's do the same thing for equation 2. Here we have minus G2 E1 plus G2 plus G3 plus G4 plus G5 E2 minus G4 plus G5 E3, that equals 0. Okay, so that's this equation rewritten in that way in terms of conductance. And finally, let's rewrite the third equation in terms of conductances. We have no E1 term, and for E2 we have minus G4 and minus G5. And for E3 we have G4 and G5. And then we throw the known current to the other side. Equals minus IS2. Okay. Now this set, let's call it set of equations star. And now finally we put that set into a form that computers like. This is matrix form. Some square matrix multiplying the vector of unknowns. In this case it's no voltage vector, and on the right hand side we have a vector of knowns. Okay. To figure out the unknown vector, all we have to do is, if you use it over here. Multiplying is to multiply both sides by the inverse of this matrix. Okay, therefore, the answer equals inverse of this matrix times the vector of knowns. Okay, let's fill in the entries of those matrices and vectors. Okay, and all we need is already on the board. Okay, the set of equations start. This is our vector of unknowns, E1, E2, and E3. And we earlier called that vector node voltage vector, E. This vector we're going to call it IS, that contains the known entries. And then here we have this matrix, whose entries will be in terms of our circuit parameters, you know, resistances in this case, and it's called YN, known admittance matrix. Admittance matrix. Okay. And now let's fill in the entries. For the first row, we look at the first equation. Okay. So we have G1 plus G2 for E1 minus G2 for E2. We have no E3 term. That means that entry is 0. And on the right hand side, we have IS1. Okay, so that's the first row of our matrix formulation. For the second row, we look at the second equation. For E1, we have minus G2. For E2, we have this big term, G3 plus G4 plus G5. For E3, we have minus G4 plus G5. And right hand side is 0. Finally, for the last row, we look at the last equation. We have no E1 term, so that makes a 0 for that entry. For E2, we have minus G4 plus G5, and for E3, we have G4 plus G5. This is minus IS2, it goes to this entry IS2. Okay. Since we have followed the convention, this node admittance matrix, okay, turned out to be symmetric. Okay. Minus G2 in this term, and the same, and 0, 0, and so on. And this is called node equations in matrix form. Now, note that in the circuit, which was formulated by an voltage analysis method, we didn't have any voltage sources. When we have voltage sources, the procedure becomes, we have to be a little bit careful about treating those voltage sources, because they, it's not straightforward to figure out the currents through them. Okay, so what we do is we don't figure out the currents through them in terms of node voltages, so we do something else. Okay, so let's see what those something else's could be. Okay, so let's see how we treat voltage sources when we try to formulate a circuit in terms of node voltages. Node analysis with voltage sources. Okay, here is an example where a voltage source seems to cause a problem, but it doesn't cause any problem at all. Okay, so that's we'll see why. IS, R1, R2, R3, R4, and here we have a voltage source, VS. Okay. Now let's formulate this circuit in terms of node voltages. Remember, the very first step, or even the 0th step, is labeling. First we choose the reference node. And note that this is arbitrary. Okay, we can choose whatever reference node we want, but sometimes some choice may be better than the other. Okay, but it's not really that important. And then we label the remaining nodes. Now, let's apply the procedure that we have written down. Okay, very recently. And if you apply the procedure, what remains once the ground node, reference node, is taken out of the picture are 3 nodes. Okay, so that makes E1, E2, and E3. E1, E2, and E3. Those are our node voltages. Okay, so formulation variables are E1, E2, and E3 if you apply the procedure. But we're going to see that this is not the best way to go with this. Okay, but still, let's forget about that at this point and then apply blindly, let's say in quotes, the procedure that we have written down recently. So formulation variables are E1, E2, and E3, and that means number of equations needed. Therefore, it's 3. Okay. So let's go ahead and write KCL at each node. Node 1, this current plus that current equals 0. This current is minus IS. Okay. Plus this current is this voltage over R1, and this voltage is E1. Okay. And this current is this voltage over R2 plus minus that voltage is E1 minus E2. E1 minus E2 over R2 by KCL, that must equal to 0. Okay, so there's no problem with the first equation. Second equation is obtained at node 2. This is our node 2. Now you can sum these 3 currents and sum must equal to 0. This current is E2 minus E1 over R2. E2 minus E1 over R2. This current is this voltage over R3, which is E2 over R3. And finally, this current is E2 minus E3 over the resistance in between, which is R4. And KCL says that sum must equal 0. And how about node 3? Try to write KCL at node 3, you will run into the following trouble. This is the node, and there are 2 currents associated to it, this current and that current. This current is easy, E3 minus E2 over R4. But this current, since this is not a resistor, okay, we cannot use Ohm's law. Since it's not a current source, we cannot directly see the current. It's a voltage source, okay? Therefore, by just looking at it, we cannot see the current, we cannot express the current in terms of the node voltages. Okay, so that's the problem that's caused by the voltage sources. Okay, now KCL does not give us a useful equation. In fact, it doesn't give us any equation at all. Okay. In terms of E1, E2, and E3 formulation variables here. Okay. But we desperately need a third equation, okay, because we have 3 unknowns. And third equation is this. Note that this node voltage, since this node is this, okay, since between this node and ground node there is a voltage source, this node voltage must equal the voltage provided by the voltage source. Okay, so in other words, E3 is no other than Vs. This is the third equation. Note that this is not the equation that need be solved. This directly gives us what E3 is. Okay? Therefore, it doesn't make sense, okay, to treat E3, the third node voltage, as an unknown or as a formulation variable. Okay? So, and that's what we will do when there is a voltage source between some node and ground node. The corresponding node voltage, we will not treat it as an unknown. We will not label it as one of our formulation variables. Okay? And that will reduce the number of equations that we have to write. So that's the lesson that we should learn from this situation. Okay. Okay. So here is Remark. When there is an independent voltage source, yes, between the ground and some node K, we do not consider node voltage EK as an unknown or a formulation variable, as one of our formulation variables. The very simple reason is because it's not an unknown. We directly know what it is. Since it is not an unknown. It's not unknown. EK equals Vs. Okay. So with that observation, let's revisit our example. Revisit. Okay, so that's what we're supposed to do in such cases. So let's see the proper formulation of this case. So this was a circuit. IS, VS, R1, R2, R3, R4. Okay, let's start from the beginning. This is the circuit that we're given. What we do labeling. Okay, choose the ground node. Okay, and then label the remaining nodes. What we did previously is we labeled this E1, we labeled this E2, and we labeled that guy E3. But now we see that introducing E3 as an unknown is just a waste of time, because E3 we directly know. We directly know that it's Vs. Therefore, we don't have to do any labeling for that node. That means we have just two unknowns, E1 and E2, and that's a great relief, because that means we need only two equations. And now let's quick write those two equations and put those equations finally into matrix form. Okay, so this is how we treat such cases. Formulation variables are E1 and E2. Okay, instead of 3, we have 2 formulation variables. And number of equations needed, therefore is 2. Now, write KCL at this node. This current plus that current equals 0. It would be same as what we have written in our first attempt. Okay. Now, how about the second equation? In our first attempt, the second equation contained 3 unknowns, E2, E1, and E3. But now we know that we don't need to label E3 because E3 directly equals BS. Therefore, what we will do is we will write the second KCL equation in terms of E1, E2, and ES, and ES is a known. And that will be enough for us to solve for E1 and E2. Okay, so what we have is this current plus that current plus that current is 0. This current is E2 minus E1 over R2 plus this current, which is E2 over R3 plus this current, okay, which is E2 minus Vs over R4. E2 minus Vs over R4. And by KCL, that equals 0. Now let's collect those two equations in matrix form. Here we have our 2 by 2 node admittance matrix. It's 2 by 2 because we have 2 formulation variables. And this is our formulation variable vector or non-voltage vector. And this is the vector where we collect the nodes. Okay. For the first row, we look at the first equation. For E1, we have 1 over R1 and 1 over R2. For E2, we have minus 1 over R2. And this guy we throw to the other side and it becomes plus IS. So that's the first row. For the second row, we look at the second equation. For E1, we have minus 1 over R2. For E2, we have 1 over R2, 1 over R3, and 1 over R4. 1 over R2 plus 1 over R3 plus 1 over R4. And this thing we throw to the other side because it's known. So we have Vs over R4. Okay. So that's how we treat cases with voltage sources if the voltage source is between ground node and some other node. Okay. Now, sometimes, well, usually, voltage source doesn't appear between node and ground node. It appears between 2 non-ground nodes. In that case, the procedure requires a little bit of modification, and now we're going to see how we treat such cases. Okay. So that's called modified node analysis. Okay. So when there is a voltage source, okay, and not necessarily independent, it could also be dependent or independent between 2 nodes, and both are different from the ground node. If one of them is ground node, then we know what to do. There's no need for modification. Nodes, let's call them A and node B. We cannot express directly the current through it but we need current because we write KCL. So what to do in terms of EA and EB? EA and EB. EA is node voltage for node A and EB is node voltage for node B. In such cases, we do either of the following. So this is method 1, and then there's a better method which is just a slight improvement over method 1, which we will see next. Okay. Method 1 is augmenting or increasing the number of unknowns, okay, by introducing the current, which you cannot express as one of your formulation variables. Okay. So that's our method 1. Let the unknown current, let's call it I, through voltage source be one of your formulation variables. Therefore, first method is increasing the number of formulation variables. Okay, so that means you will require more equations, which is not a great thing, but if it's computer that's solving it for you, then it's not a big deal either. Okay, here is a situation which requires such modification. Okay, so here we have the voltage source, resistor, another resistor, another voltage source, another resistor, another resistor, and a current source. Plus minus. This is VS1, this is VS2, R1, R2, R3, R4, and R5. This is IS1. Okay. So this is, suppose, the circuit that we want to formulate in terms of node voltages. So what we do, as we said before, the first step is always labeling properly. Choose a ground node. So that is our ground node, and then label the remaining nodes. So the remaining nodes are here 1, 2, 3, and 4. So what we do is we start labeling. So we don't label this node not as E1 because between this node and ground node, there is an independent voltage source. That means we directly know what that node voltage is. Therefore, this is not an unknown. Since it's not an unknown, it's directly known. We don't need to label it as one of our node voltage. So we start labeling from this node. So this is our E1. Then we have E2. Then we have E3. Okay, we have 3 node voltages. Now, since there's a voltage source between node 1 and node 2, there's a problem in expressing this current. Okay, because we cannot apply Ohm's law because it's not a resistor. We cannot write the current because it's a current source. It's a voltage source. We don't know what the current is directly in terms of node voltage. Therefore, what we do is, or what's suggested here under method 1 is, since you cannot express that current, just leave it as an unknown and do not try to express it. Okay? So let this current be I. And now, formulation variables are, we have known voltages, E3, but on top of them, we also have an additional unknown, which is the current that we cannot express in terms of them. Okay, R. So we have 4 formulation variables, so that means we require 4 equations. Okay, so let's go ahead and write KCl at each node. Node 1. This is our node 1. This current plus that current equals 0. So let's write that down. This current is this voltage over R1, and this voltage is E1 minus this node voltage, and this node voltage directly is Vs1. So here we have E1 minus Vs1 over R1. Okay, that's that current. Then plus that current, which is E1 over R2. Then plus this current, which we realize we cannot express directly in terms of E1 and E2, so we just leave it as it is, plus I equals 0. So that's our first equation. Node 2. Okay. Now we're summing these 3 currents. This current is minus I. Okay. And then we have this current plus E2 over R3, and finally we have that current, which is E2 minus E3 over R4, and by KCl that's somewhat equal to 0. And we have just one node remain. Okay, remain. So let us also write KCl at that node. So we're summing up this current, and that current according to our convention. So this current is E3 minus E2 over R4 plus this current, which is minus IS1 and finally plus that current, which is E3 over R5 equals 0. Okay. So everything is nice. Without any problem, we have been able to write down the currents, because we don't now try to express this I in terms of node voltages. Now, here there's a problem. The problem is the following. All these equations are, in terms of our formulation variables, they're fine, they're legitimate, okay? But the number is 3. Okay, we have 3 equations. However, we have 4 unknowns. That means we require 1 further equation. And that equation will not be coming from KCl. In this case, it will be coming from KVL. Okay. Now that this Vs2 is the voltage difference between this node and that node. Okay. Therefore, that voltage source puts a constraint through KVL on the relation of E1 to E2 or E2 to E1. Simply, E1 minus E2 must at all times be equal to Vs2. So that would be the missing 4th equation, which we call the constraint equation. E1 minus E2 equals Vs2. Note that Vs2 is known because the voltage of an independent voltage source. Now we have the right amount of equations. We have 4 equations. Hence, those equations are enough to obtain the answer. Okay. Let's put everything in matrix form and end today's lecture. In matrix form, now we have, since we have 4 unknowns, that means this matrix will be a 4 by 4 matrix, okay? And this is our vector of unknowns, E1, E2, E3, and this current, which now we consider also as one of our formulation variables. This is the vector that will contain the known knowns, and this matrix will be in terms of our matrix circuit parameters. Okay. For the first one, let's look at the first equation. We have for E1 1 over R1 plus 1 over R2. For E2 we have nothing. For E3 we have nothing. For I we have 1. And we throw what remains to the other side, and what remains is ES1 over R1. ES1 over R1. Okay. For the second row, we look at the second equation. For E1 we have nothing. For E2 we have 1 over R3 plus 1 over R4. For E3 we have minus 1 over R4. And for I we have minus 1, and nothing remains for the right hand side. For the third row, we look at the third equation. Okay. For E1 we have nothing. For E2 we have minus 1 over R4. For E3 we have 1 over R4 plus 1 over R5. And for I, we have nothing because it doesn't appear in that equation. And finally, we throw this known to the other side. So it's I as well. And the last row is reserved for constraint equation. Okay. For E1, we have 1. For E2, we have minus 1. And for E3 and I, we have 0. And the right hand side is ES2. Okay. So in our next lecture, we will see a similar but a little bit improved version of this first method under the title method 2, in which we will be able to formulate the circuit without requiring to introduce an extra formulation variable.